Good morning and welcome to my YouTube channel. I am Arthur Francis Divan. Please don't forget to subscribe and press this notification button. Today we'll be dealing with qualitative organic analysis, like we did in the previous class was qualitative inorganic analysis. Today is organic. So qualitative organic analysis is an aspect of practical chemistry that is concerned with the identification of various elements and functional groups present in organic compounds. So see, this one we identify certain elements and majorly their functional groups. The functional group defines the compound. For example, in a compound that contains OH, we're looking for the hydroxyl group for alcohols, or COOH for alkanoic acid, and so on and so forth. Now, functional group is an atom or group of atoms which gives its own characteristic chemical behavior to a homogeneous series. So a functional group distinguishes that compound 100% completely from another compound. So if you have a compound that contains OH, like I said earlier, and another one that contains COOH, you will know that this one is for carboxylic acid because of the functional group, and this is for alcohols because of the word functional group, and so on and so. The aldehyde, the ketones, all of them have various functional groups. All right. Now, we will have to, in due time, go on forth to know our various functional groups. But for today, we want to carry out the various tests in order to identify the functional groups. So we have the preliminary test and solubility, like we did in the previous one about this preliminary test, which include the physical state, smell, and action of heat. So we look at the physical state. In the other one, through the physical state, we're looking at the texture, which has to do with the crystalline and amorphous form of the compound. So here, again, we're dealing with almost the same thing, which is the physical state. Now, here, in the physical state, we have a compound exists as solid and liquid, all right? Solid and liquid majorly in organic qualitative analysis. So let's look at liquids first. This includes hydrocarbons, compounds that contain carbon and hydrogen, alkanols, the OH group family, carboxylic acid, esters, amines, aldehyde, and ketones. All of these are what in their liquid, they appear or exist in what their liquid form. So when I bring a compound to you for analysis, for example, and it is in its liquid form, the first thing that comes to mind is this compound will either be what? Carboxylic acid, alcohol, amine, esters, and so on and so forth. Your mind goes there, basically. Then for solid, we say this includes salts of organic acids and bases, aromatic acids, carbohydrates, proteins, etc. So I said earlier on that in the preliminary test, which include the physical state, which I've just discussed right about now. So the next one is the smell. Now, from the smell, we'll be able to identify the compound that also exists, the organic compound that exists through the smell. Let's say some organic compounds can be identified by the peculiarities of their smell. Example, esters, which we know have a sweet, fruity smell. So when you perceive that fruity smell, you know that it is esters. And amines have fishy odors. Amines have what? Fishy odor, like fish, smells like fish. So action on heat, we also did that in the flame test when we're dealing with the inorganic qualitative analysis, where we have to use nichrome wire or platinum wire, get a little of it in a watch glass with HCl, hydrochloric acid, then subject it to the hottest part of the flame. It gives you a peculiar word, color. So here, action on heat, we take a little of organic compound on nickel spatula and heat. When we take a little of it and what we heat. Now, A, if the substance burns with non-sooty and or non-luminous flame or non-smoky flame, indicate the presence of aliphatic hydrocarbons, such as saturated hydrocarbons. They have single bonds. All right, there's this it could be straight or branching, as the case may be, but they are all single bonds. So how do we identify them? When we heat them, we say the substance is bound with non-sooty or non-luminous what? Flame. But if the substance burned with smoky or sooty flame indicates that the substance is unsaturated, that is, it is double bond or triple bond, or aromatic, benzene, anthracene, naphthalene, or contain high carbon to hydrogen ratio. So these are the conditions. So now by the action of heat, if I should subject a substance to heat and it gives me a non-sooty flame, I know it's saturated. If it gives me flames, okay, then we say it is what? Unsaturated. That's smoky flames. So the last one here is the solubility. How then also are we going to identify an organic compound that has been given to us? We have to carry out what? The solubility test of that particular compound by dissolving it in various substances. So various organic compounds or functional groups will dissolve in various what? Solvents. So let's look at it. Now, the presence of a functional group of an organic compound can be detected by the solubility of the compound in a given solvent, depending on the functional group. An organic compound can dissolve in any of the following. These are the following stuff which an organic compound can dissolve. 1. Water. 2. Ether. Saturated sodium hydrogen trioxocarbonate 4 solution, dilute sodium hydroxide, and dilute HCl. Let us see. 1. The first one is water. Let's see what kind of organic compound dissolves in water. When soluble organic compound dissolves in water, it gives either acidic solution, basic solution, or neutral solution. Now, based on the type of solution formed, an organic compound can be identified if A. Acidic solution is formed. Then the following are present. How do you know it's acidic solution? After you have dissolved it, okay, you use your litmus paper and dissolve or immerse it into the what? Solution. If it turns blue litmus to red, it's acidic. If it turns red litmus to blue, it is basic. If it doesn't change, it's neutral. So that's how you know. So a substance has been given to you to run your practical test. First thing, you dissolve it in water. Then you stir it, probably it has dissolved. You want to certify whether it is acidic or basic or neutral. You use your litmus paper to test that. So we say if it is acidic solution, after we have identified acidic solution, we say then the following are present. Alkanoic acid, salt of alkanoic acid with weak bases, and salt of amine with strong acid. B, if it is a basic solution, the following are present: amine and salt of alkanoic acid with strong bases. C, if it is a neutral solution, the following are present: alcohols, aldehydes, ketones, amides, and carbohydrate. So when we dissolve in these various solvent and we certify whether it is acidic, basic, or neutral, this is how we identify to proceed further as to what the compound that exists therein and its what functional group. Now, remember we talked about water when we dissolve them in water. So now let's look at ether, which was the second one. Now, if organic compound is soluble in ether, we can infer the presence of non-polar organic compounds such as naphthalene, starch. Non-polar means it's not soluble in water. So those are what? Naphthalene and starch. Now the third one is saturated sodium hydrogen trioxocarbonate 4 solution. Now, if organic compound is soluble in saturated sodium hydrogen trioxocarbonate 4 solution, it indicates the presence of alkanoic acid. So that one is just straight up, alright? So we can line up these various solutions or solvent, or let's call them solutions. And the sample that has been given to us, we divide it into different proportions. If I dissolve it in water, it doesn't. I dissolve it, try it in the next one, try it in the next one. Like for example, if you dissolve in sodium hydrogen trioxocarbonate 4, you just say, it's acidic, it's carboxylic acid that is present therein. So the fourth one is dilute sodium hydroxide. If organic compound is soluble in saturated sodium hydrogen is soluble in dilute sodium hydroxide, then alkanoic acid and phenol are present. Phenol is a benzene ring with OH group attached to it. Now, the fifth one, which is a dilute HCl. If an organic compound is soluble in dilute HCl, then the inference is that amine or basic organic compounds are present. So that's just straight up, all right? So from here, we've been able to get our preliminary examination on how to know the functional group that is present therein in a given substance or sample that will be given to you. We do various functional groups. It could be carboxylic acid, it could be alcohol, it could be amine, it could be ester, and so on. At various levels, through solubility, we can determine that. Through the action of heat from this sooty or non-smoky and all that, we can still determine that. And through the physical state, we can also determine that. So that is basic knowledge, which we should have in our mind before we get into the practical hall, so that whatever we're doing becomes easy. Now, the second category, which is very important, we're going to deal with them stepwise. Now, how do we test for functional groups? Maybe you do not have a vivid knowledge or elaborate knowledge on the solubility procedures or the physical state or the action on heat. No, but there are various other procedures which you can use to determine the various functional groups present in various compounds. So let's see if we're testing for saturated hydrocarbon like alkane. So the alkane, saturated, we have the single bonded. We have methane, ethane, propane, butane, and so on. Hexane, heptane, octane, nonane, decane, and so pentadecane, many more. So if all of these, they are all single bonded. But we want to find out what kind of test are we going to carry out to determine that it is saturated first to begin with, all right? Now we say the sample plus bromine water and shake. When we shake, we say no visible reaction. Maybe I should write that down so that we'll be able to look at them religiously or carefully. So let's take the first one here. So in the first experiment here, we are to confirm the functional group present. So what we're dealing with, the single bonds, which are saturated hydrocarbon. We have many of them. We have methane, ethane, propane, butane, hexane, and so on. So let's say, for example, I've given you a sample of hexane for you to run your test to confirm as to know whether it is single bonded or thereabout, but I will call it sample A. You don't know what is inside. It's just named sample A. So that sample A plus bromine water and shake. When you shake it, no visible reaction. Alright? When there's no visible reaction, it gives you saturated hydrocarbon. It's confirmed. Or that sample A, or whatever it is, plus dilute H2SO4, which is acidified now, plus KMnO4 solution, no visible reaction. And there's still no visible reaction. Saturated hydrocarbon is confirmed. So, saturated hydrocarbon, like the hexane and so on, have no reaction at all with bromine water or with KMnO4 solution. This will not be the same with other functional groups. So, that is the first one. So, let's take for unsaturated hydrocarbon and see what we get. Yes. In that of saturated, we use almost the same samples here. We got the reactions. There was no reaction when we used bromine water, no reaction when we used KMnO4. That shows that it was saturated hydrocarbon. But in this case, test for unsaturated hydrocarbon. How do you know that it is unsaturated? The same sample plus bromine water, or that sample plus bromine water, and you shake it. Brown color of bromine water decolorizes. So the brown color will become decolorizes, clear. So you know that it is unsaturated hydrocarbon, because unsaturated hydrocarbon decolorizes bromine water. Now, the sample plus dilute H2SO4 plus KMnO4 and shake, just like in that of saturated when we're dealing with hexane. Now, the purple color of KMnO4 also decolorizes. That unsaturated hydrocarbon still confirmed. Now we move further. The sample plus ammoniacal copper 1 chloride solution, and we shake. No visible reaction observed. Double bonds confirmed, because in the double bond that doesn't react with ammoniacal copper 1 chloride. That doesn't. So now we know that the unsaturated, because unsaturated hydrocarbons have two classes, the double and the triple bond. So now we'll be able to confirm that it was the double bond that was reacting and not the triple bond. And so on, we'll proceed until we get to finish and see that what happens if it is the triple bond. So let's go further. All right, here again we go. We have the test for unsaturated hydrocarbon alkyne, to be precise. So we have the sample plus bromine water and shake. Brown color of bromine water decolorizes. Unsaturated hydrocarbon confirmed. B, the sample plus dilute H2SO4 plus KMNO4 solution and shake. Purple color of KMNO4 is decolorized. Unsaturated hydrocarbon confirmed. The sample plus ammoniacal copper 1 chloride solution and shake. Yellow precipitate produced. Triple bond hydrocarbon confirmed. So let's look at the difference here. The A and B reactions are the same with the double bond. But the difference is in the triple bond, in the reaction with ammoniacal copper 1 chloride, where we're dealing with the alkene, which is the double bond, there was no reaction yet. The yellow precipitate produced wasn't there. There was no reaction, but yet there was a reaction. So in our quest of finding out the various functional groups for the saturated hydrocarbons, we reacted the same sample plus bromine water and shake, no reaction. Saturated hydrocarbon confirmed. We did the second thing with KMNO4, there was no reaction. Saturated hydrocarbon confirmed. For the double bond, there was a brown precipitate which that was decolorized, that of bromine water, and the purple color of KMNO4 was decolorized. Both unsaturated hydrocarbons were confirmed. When we proceed further to react with ammoniacal copper 1 chloride, there is no reaction when it is double bond, and there is a yellow precipitate when it is triple bond. So by so doing, you will be able to know if it is double bond, triple bond, or single bond. So let us look at tests for alkanols. So test for alkanols, which is the OH group. We say to the sample, we should add few drops of concentrated H2SO4 plus ethanoic acid plus heat. A sweet fruity smell of ester is formed. The gas is hydrogen. OH is confirmed. So it confirms that it is what? An alkanol or alcohol present. Remember our reaction, esterification reaction, where we react the alkanols with alkanoic acid in the presence of H2SO4, which acidifies it. In the course of that reaction, we always get esters formed. And since there are esters to be formed in the process, we always have a sweet, fruity smell, which is a characteristic word test for what? Esters. So that is for alkanols. So move further to another functional group. Okay, test for the carboxylic group. We say the sample plus corn H2SO4 plus alcohol plus heat. We still have our sweet fruity smell of ester is formed because the reaction of alcohol with a carboxylic acid, alcohol with carboxylic acid, the presence of H2SO4 always give us esters and water. So ester will be formed, CO2 is confirmed, COOH is confirmed. Now the sample plus saturated solution of sodium trisulcarbonate 4, effervescence occur, colorless, odorless gas which turns blue litmus paper red, and lime water milky is evolved. CO2 is confirmed because CO2 almost in all cases turns lime water milky, and as such carboxylic or alkanoic acid is present. So we're going to look at another functional group. Remember, we have to put this thing in our head because in the course of our reaction, when we start carrying out the practicals, we have to remember that when we put this, the observation is supposed to be this, and when we come across the observation, we know exactly what we are testing for. Now let's test for alkanol. Alright, in test for aldehyde, that's the alkanols, example, an aldehyde, we say the sample plus saline solution, the brownish red precipitate is formed. So once we get this, we know that we're testing for aldehyde. Aldehyde functional group is confirmed. The sample plus Tollens reagent, when we react an aldehyde with Tollens reagent, a silver mirror is formed on the side of the test tube. Aldehyde functional group is confirmed. So the two tests we carry out for aldehyde, we run it with saline solution, we get the brownish red precipitate is formed. We run it with Tollens reagent, we have a silver mirror formed on the side of the wall of the test tube. So in both cases, aldehyde was functional group confirmed. So let's see alkanones. So if we're done with the aldehyde, let's look at the alkanones. So for the test for alkanones, which are the ketone group, we say the sample plus iodine solution plus sodium hydroxide, yellow precipitate of iodoform is formed. Ketone functional group present. The sample plus phthalate solution or Tollens reagent, no effect. Once there is no effect with these two guys, we say ketone functional group may be present. Let's see if we still have more to do with. Test for phenols. Alright, let's do that of phenols. At least one more. Now for phenols, the sample plus iron 3 chloride, purple or violet coloration, phenol is present. B, the sample plus bromine water, white precipitate is formed, phenol is present. Let me